Okay, let's take a minute to review some chemistry. What I want to focus on now is atomic structure and bonding. Um, so if you recall from lecture, there are protons and neutrons in the nucleus of an atom, and then the electrons are orbiting that nucleus. So we identify atoms based on their number of protons. It's one of their identifying features. And if you look on the periodic table, there's an example of one. It's Appendix A in the back of your book. On the periodic table, let's pick an atom, let's say carbon. If you look in the square that has carbon, it has a C to symbolize carbon. There is going to be a 6 at the top of this particular square. Now, some different tables may organize the atomic number or the number of protons in a different fashion, but in our book, the 6 represents the number of protons. So let's start drawing our atom. We have 6 protons in the center of the atom. Also in the center, in our nucleus, are going to be our neutrons. How we find our neutrons, the number of them, is also through the periodic table. On the periodic table, there's going to be a number. It's not a whole number. In carbon's sake, it's 12.0112. It's not an exact number. So we round to the closest number. We're going to round to 12. This is our atomic mass, or AMU. Atomic mass is the number of protons plus the number of neutrons together. So we have our atomic mass, the two of them together. In order to find the neutrons, we subtract the number of protons. So we had our 6 protons. So 12 minus 6 is 6. So in this case, we happen to have 6 neutrons as well. So we'll draw those in here. So we have our nucleus with our protons and our neutrons. And the next step is finding where our electrons are going to be orbiting around the outside of the nucleus here. Protons are really, really tiny. Their weight is basically negligible. That's why they don't get considered in the atomic mass. But when you look on the periodic table, all of our atoms on the periodic table are considered neutral, meaning that they have the same number of protons and electrons. So if we know our atomic number is 6, and it's a neutral atom, we're going to have 6 protons and 6 electrons, so the charges cancel each other out. We have a bunch of energy levels around our nucleus. The closest one to it can hold 2 electrons. Once that one's filled up, we'll move out to another energy level. This particular energy level can hold 8. When it's filled up, if there's any more electrons, then we'll move on to another energy level, and another, to fill them all up. The second and remaining energy levels, if there are any, all of them can hold up to 8 electrons. So let's start filling up our orbits with our electrons. We have our first orbit, so we can get 2 electrons in here. So we've used 2 of our 6 electrons. We've filled up the first energy level. Now we need to go to the second one. We have 4 remaining electrons. So this is how we would draw our atomic structure of a carbon atom. Now what if we wanted to draw another atom? Let's say oxygen. Oxygen is going to be very similar. It's going to have 8 protons and 16 as the atomic mass. So if we hit join, get our little protons in here. So we got our 8 protons, 1, 2, 3, 4, 5, 6, 7, 8. That was the atomic number of 8 that I found on the periodic table. Let's make them a little darker. We know the atomic mass is 16. So in order to find the number of neutrons, we're going to subtract our 8 from our 16, which would give us 8 neutrons. 1, 2, 3, 4, 5, 6, 7, 8. All right, now we need to fill up our outer shells, just like we did with our carbon. So we'll start our bonding here. We start the same way. We have 2 electrons on the first energy level, so we've used 2 of our 8s. Now we can put 6 in the outer level. So this is how we would draw 2 of our particular atoms. Now, the nice thing about carbon and oxygen is that they often like to do covalent bonds. If you remember, covalent bonds are very strong bonds, and it's when they share electrons. They work towards filling their outer energy levels with 8 because that makes them stable. Covalent bonds allow them to fill their outer shell without giving away any particular electron. It's when 2 atoms really have this nice kind of middle ground and they don't want to give up any of their electrons. So they're going to really fight to hold on to them. And carbon and oxygen do that. So we're going to show, how would you show them bonding with each other? If they're going to share electrons, what we would do is we would have these energy levels overlapping here. So it's still the second energy level, and they would overlap one another. And this is where they would we would designate their shared electrons. Maybe one shared from carbon and one's shared from oxygen. So we have this covalent sharing of electrons. This makes it a very, very strong bond. Also referring back to our periodic table, sodium has an atomic mass of 23. So 23 minus 11 is going to be 12. So we're going to put it in 12 neutrons. All right, now time for our electrons and our orbits. Again, we're going to start by filling the exact same way. We'll start with our first energy level. We're going to need a total of 11 electrons. Remember, we have a neutral atom here where we have the same number of protons and the same number of electrons. That's how we always start. So we have 2 on the first energy level, and then we need to fill up the second energy level with 8. And that only gets us to 10 electrons. We have 11. So we're going to have to go out to one more energy level. where we have our single electron, our valence electron. The number of electrons in our outer shell is going to be 1. If we look at chlorine, chlorine has an atomic number, or number of protons, of 17. So 17 protons in the nucleus. We have an atomic mass of 35. So that leaves us with our neutrons here. 2, 4, 5, 6, 7. 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 17, 1 more, 18. So 35 minus 17 is going to give us 18. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So our 18 neutrons hanging out in the nucleus with our protons. Now we need to start filling in our orbits. Again, we're starting neutral, so we have the same number of protons and electrons. There's 2, so we have 15 more we need to fill in. So we filled up the first 2 shells and we've gotten to 10. So we have quite a bit more that we can fill in. So we have 17 more electrons that need a place. One, 2, 3, 4, 5, 6, 7 electrons in our outer shell. Now, with these atoms, they're a little bit different than our carbon and our oxygen that we just looked at. Carbon and oxygen had this nice centralized, even almost number of electrons. It was going to be easier for them and less energy costly to keep them, and they really wanted to hold on to them. For sodium here, it has 1 electron in its outer energy level. It's a lot of work to keep this energy level open and functional for 1 electron. So energy speaking, it's going to want to get rid of it. It's going to be much more efficient to get rid of that electron. Our chlorine over here, on the other hand, has 7. It has pretty close to full, and actually atoms want to be full. They want that outer layer, that outer energy level to be full with 8. It's energy efficient for them. So our chlorine wants to get that other electron. It wants to fill up. What happens is then we become ions, where our sodium here will give up its electron and give it to chlorine. So sodium is going to give up chlorine. Now because we've lost an electron, we now have more positive charges. This makes sodium positive, and chlorine has gained an electron, so it has more negative charges, and this makes chlorine negative. How these two like to bond in together is almost how like magnets are attracted. The positive and a negative get attracted to each other. In comparison to our covalent bond, this is weak. This is not very strong and can be easily broken. So here we have our ionic bonds, that's transferring of an electron from one atom to another that creates this attraction between them because of the difference in positive and negative charges.